Oh, hi, you're here for the HPC class, right?
Yes.
Well, I'm at the right place. Um,
Recording in progress.
um, Hey everyone, how many people do usually come to class?
I'll say 5, 6 more.
Nice. So it's better to wait some more.
7, more students. Sure, I guess, but I think it's raining, so that's why it's gonna be online.
Yeah, they also like sent the link online particularly, so I think.
Oh, there's a bunch of people. It is 5 p.m. already. I will go ahead and start. Hi everyone, my name is Muhammed Fatih Balin. I am a PhD candidate at Georgia Institute of Technology here, same as you, working with Ümit Çatalürek. My thesis topic is on scaling graph neural network training on multi-GPU systems. And today I will talk about the algorithms that I have come up for this purpose so far, and also the systems optimizations I have been doing for the Python package called dgl.graphbolt. So let's start with some motivation for graph neural networks. So so for people online, am I audible? I just wanted to make sure. Let's start with our motivation. So you can use graph neural networks in many applications. One obvious application is online shopping, where if you go to Amazon, for example, and you're looking at some items, as you purchase items, the algorithm there might be able to learn your preference, and in the future might be able to recommend you items that you may be more inclined to purchase. And for example, on social media, if you are using it for a while, if it learns your preference, then it can give you a better news feed. You can use graph neural networks for that purpose, or it can also recommend you to follow some people or become friends with some people because it has learned your likes and it has learned about your existing friends. It can also do content recommendation. For example, if you're listening to music or watching videos, it can learn your preference there too. Like you can think of it as you are, as a user, you're a vertex, and the things you consume, such as music or video, they are vertices too. And whenever you click on them or whenever you interact, you can think of it as an edge between those two vertices. And finally, you can also use graph neural networks for showing users relevant ads so that they are more likely to click on it to increase the profits for your application. So let's start with a basic recap of graph neural network. So here we see a vertex 0, and we see that there are 2 layers. So in order to compute the message or the embedding for vertex 0, we need its neighbors, and we need messages coming from its neighbors. So here in this case, the neighbors are 1, 2, and 3. And here you can see that because we have 2 layers, we need their neighbors too. So in recursively doing this for each layer you have, you can see that there is an exponential growth. And this is very bad for scalability. Like if you want to just compute, if you just want to compute the output for a single vertex, you can see that it becomes exponentially hard as there are layers. So for to reduce this computational burden, you can utilize sampling. So what you can do is, instead of utilizing the whole neighborhood during training, for example, because during training you can approximate things and it's still, the model still continues to learn. So what you can do is you can sample the neighborhood of 0 and recursively do the same for its neighbors. Like you can sample the neighborhood of 2 and for example, drop 7, and for 0, we have dropped 1. And the whole, because it's recursive, when you drop a vertex, because it's recursive, you drop the whole neighborhood that they have too, which helps with scalability tremendously. So let's talk about some sampling strategies that one can use. So the simplest strategy is node-based sampling, where given vertices 1 and 2, you want to sample 2 neighbors for each. So how can you do that? So you look at one's neighbors, they are 3, 4, and 5. And if you want to sample 2 of them, then what you can do is just you can randomly pick 2. And then for 2, you do the same. Among 4, 5, 6, you pick random 2 neighbors. But if you do this in an independent way, and by the way, if there are any questions, feel free to interrupt so that we don't pass over things without a clear understanding. So when you do this sampling process independently for 1 and 2, you can see that even though they have some common neighbors, they ended up sampling different neighbors. So in the end, there is no overlap. So for example, for 1, we have sampled 3 and 5. For 2, we have sampled 4 and 6. And because there is no overlap, this exponential growth for the later layers will be, the growth will be much faster. An alternative is to utilize layer sampling. So what you do is, given 1 and 2 again, you look at all their neighbors combined. So all their neighbors are 3, 4, 5, 6, 7. And then what you do is, among these 5 vertices, I want to pick 2. So you pick 2 of them randomly, 4 and 5. And then after that, what you do is, you incorporate all the edges between 4 and 5 and 1 and 2. And you can see this way, we have naturally more overlap because we have selected some overlapping neighbors. So even though we have picked only 2 neighbors, both 1 and 2 still have 2 edges each. And we can skip the subgraph version for today. Yes?
So basically we just sample from the intersection, right? Of 2 vertices, kind of.
Not intersection, the whole union. The union is 3, 4, 5, 6, 7.
Mhm.
And we have 5 vertices there. This is the union of their neighborhoods.
Okay, I thought the idea is that we want to kind of like want to make sure that we have the same vertices, right? And
Yeah,
why would we?
But if you do it in a biased way, then it will be biased. In machine learning, if you want to approximate something, you should do it in an unbiased way. So there should still be a chance that 7 will be picked. Otherwise, the model that you're training, it's not gonna converge to the same place as the non-sampling version.
Yeah, that's fair. I just didn't get how the first thing that you told us and the second thing different then. Like, why did we end up in the first scenario sampling 3, 4, 5, and 6, and in the second one then only 4 and 5? What's the condition there that makes sure that?
I see. So in this case, it's just some random luck. But think of it this way. So in order for us to get the same outcome as the layer version, this needs to happen. So 1 needs to sample 4 and 5. 2 also needs to sample 4 and 5. Like, this is very unlikely to happen because we are performing the sampling process independently for these 2 vertices. But when you do this sampling process, like you take the union and you pick 2 vertices, it's much more likely to get overlap this way. Okay, cool. So next we have the graph neural network stages. So what you do first is, given some set of vertices, you need their neighborhoods first. So if you have 3 layers, for example, then you need their sampled 3 hope neighborhood. Then for those things you have sampled, all the vertices you have in your mini batch after the sampling process, you need to load the features for all those vertices. And only after that, you can start the forward and backward passes. So what you do is, you have already brought all the data. Now you can do the computation like you can start from here, for example, if you have all the data for 0, 8, 8, 9, 2, 3, and 0, then you can do the forward computation. You can pass messages from 0, 8 to 2, and then from 2 to 0, etc. So we have 3 stages. First, we need to perform the sampling of the neighborhood, 3 hop neighborhood if you have 3 layers. Then we perform the loading operation. those vertices will have some kind of features. You can think of it as a huge tensor, and then we can finally perform the forward-backward computation. And the key insights here are these are all memory-bound operations. Like for example, the graph accesses, you just access it once, so it's memory-bound. And also, let's say you have the vertices already. Now you need to fetch the features for those. That is memory-bound too. You just need to access it, and then you need to fetch it. So these are all memory-bound operations, and accelerators such as GPUs have really fast memory. So if we can use GPUs,
So one small question, do we resample in every epoch?
yes, like in every iteration, you are given a random mini batch of vertices. Like for example, if you have some training set, then you randomly pick some vertices as the seed vertices, and for those you perform the recursive sampling operation. And then after that, you perform the feature fetch operation so that you have all the data needed for the forward and backward computation.
So in each iteration, only seed vertex are updated.
Yeah. You only compute the loss for those seed vertices, but you need all the neighborhood and all the features for the neighborhood to be able to do that. So now let me tell you about the outline of my talk today. First, I will talk about a new sampling method for this purpose. It's called layer neighbor sampling. It was just published this December at the NeurIPS conference. Next, I will talk about cooperative mini batching. It is a way to utilize multiple GPUs as if they are a single GPU to reduce redundant computation across those GPUs. And next, I will talk about how I have already incorporated some of these ideas and how I am planning to incorporate these ideas into an efficient GNN training system in a Python package called dgl.graphbolt. It's like DGL stands for the Deep Graph Library. It's one of the most used GNN packages out there. And we are building a new data loader utilizing these algorithms.
So I was wondering, how would a feature vector look like in case of GNNs?
Features?
How would a feature vector look like? Can you give an example?
Let's say there are 100 million vertices. They might have like features that are each 1024 dimensional. Then it's just a tensor matrix of dimension 100 million times 1000. But these features might be computed from, let's say you have some archive papers. So there you have the paper content, right? What you can do is you can process the paper through like a large language model, for example, and you can generate these embeddings that you can later use for GNN training, for example. So those features come from somewhere else. It could, like one example is to use other types of models to generate those embeddings, which you can then later use for the GNN purposes. Does it make sense?
We don't update those features in GNN training.
You can, but let's assume today that you don't. Today we are going to talk about the kinds of models that you don't update, but even if you needed to update it, it's just the same, like it's just a detail. Okay, let's start with some background. So here we have some notation for the graph. So G stands for the graph with vertices V and edges E. And most importantly here, T stands for a source vertex, and S stands for a destination or a seed vertex, and T to S represents an edge between them. And a capital S means a set of seed vertices. Usually it also has the upper script, like it tells you for example, S0 stands for the seed vertices, and SL stands for the vertices you get after L-hop computation. And D stands for the degree. And we also have the notation for the embeddings and the GNN layer. So capital H stands for embeddings, F stands for the GNN layer at layer L, etc. And M stands for messages. Oh, here we have some. And finally, K stands for the fanout parameter, or how many vertices, how many edges we want to sample for each seed vertex. So now that we have that out of the way, let's talk about the modern computer hardware. So here you can see the common bandwidths and the storage capacities of components in a modern PCIe-based multi-GPU computer system. So here, for example, if we look at the storage components, we have the SSD. It can have a lot of memory, and you can have multiple of them. But usually, the higher the capacity, the slower it is. And next, you have the system memory. Like in a industry grade server, you can have as much memory as 2 terabytes, for example. And if you have a GPU, then it might have up to 80 gigabytes of memory. And below, you can see the bandwidths of these storage components and also the interconnects existing in the modern computer hardware. So for example, one PCIe lane has the bandwidth of 2 gigabytes. And an SSD works on 4 of those lanes with up to 8 gigabytes of bandwidth. So you can, for example, read 8 gigabytes per second from an SSD under the ideal conditions. And if you have a GPU, the GPU's connection to the CPU is through 16 such lanes, which can have up to 32 gigabytes of bandwidth. And the system memory, for example, has 400 gigabytes of bandwidth. The GPUs, if you have multiple of them in your system, they might be able to talk to each other at 300 gigabytes per second. And finally, the GPU's its own memory, it can access it at 2 terabytes per second. So if you want to make something run fast, you need to be able to utilize the fastest memory available. But as you can see, the fastest memory is usually the smallest. So you will have trouble fitting your data there. So in order to be able to get good performance, you need to have good kind of caching algorithms.
Sorry, but by system memory, you mean DRAM?
The RAM, yes.
Isn't 2 TB a lot of DRAM?
There are systems with more than 2 terabytes, but like 2 terabytes is like a common amount of RAM. In let's say the NVIDIA has DGX A100 servers. They have 8 GPUs, and those systems might have, by default, they have 2 terabytes of memory.
Okay, that makes sense. But then,
Do you generally use these type of servers?
to train things, or is it like more commercial level hardware, but more number of it?
Yeah, this is commercial level hardware. And usually if you train any kind of AI, and if you have the money, then you can buy such systems to do your research or do your training on any type of model you want. In my own research, I also work on such a system.
What's the link between GPU to GPU? Is it PCIe or NVLink?
It's NVLink. Yeah. So if it was over PCIe, then it would be much slower.
Yeah.
So here we have an example interconnect topology of such a system. Here the SSD is missing, but we have the CPU and the GPUs and the interconnect between them. So here you can see we have 16 GPUs, and these GPUs are connected to PCIe switches, and then they are connected to the CPUs. If you have 2 sockets, then you might have two CPUs, and half of the GPUs will be connected to one socket, half of the GPUs will be connected to the other socket. And here, usually the bottleneck is the connection between the GPU and the CPU because of the PCIe switches. So if you are optimizing your software, you need to prioritize your transfers over these PCIe switches so that your code can run fast and you can utilize the vast amount of memory available on the CPU and the SSD, even if you are writing GPU based software. So now we can start to talk about the layer neighbor sampling algorithm, which in short we say labor. So our goals are to perform unbiased sampling so that when you are training a GNN model, it is expected to converge to the same place as not performing any sampling. And also, we want to get overlapping neighborhoods between the vertices we have in our mini batch. And finally, we want to ensure uniformly good approximation. NS here stands for the independent way of performing sampling. So we want to ensure everybody gets enough neighbors, but also we want to ensure that they also get overlapping neighbors. So how can we do that? We can perform Poisson sampling. So what we do is we roll a random number between 0 and 1, and then we threshold it with, we check if it is less than or equal to some threshold. And if we can combine this layer and the neighbor sampling methods, then we can get the best of both worlds labor. So how can we do that? So let's do some GNN sampling background here quickly. So here you can see that for a given vertex S, to compute its output, we need to pass messages from its neighbors T, and we need to average them. For example, this is the simplest GNN model. And to approximate that, what neighbor sampling does is, for a given S, it samples a K subset of its neighbors, and then it approximates this calculation using those sampled edges. For layered sampling, as we already talked about, given some set of seed vertices capital S, we take the union, and then we sample some of those vertices and extract the induced subgraph between the sampled vertices and our seed vertices. And the way labor works is, given seed vertex S and a random number for its neighbor T between 0 and 1, we sample it only if the random number is less than or equal to K over ds, where K is the number of edges we want to sample, and ds is the degree of the vertex S. So yeah.
Right, isn't K and D the same? Because K is the outgoing edges, and you said D is also the outgoing edges? Or where's my misunderstanding?
So K is how many edges we want, and D is how many edges there are.
I see, okay.
And if we want to have K edges, if we perform this kind of operation, then we will get in expectation K items, because the threshold we use is K over ds. And if you do this for each edge you have, in expectation K over ds times ds, you get K edges.
That makes sense.
And you can make this also deterministic, because if you do this kind of thresholding, you may sometimes sample more than K or less than K edges, because you are flipping coins for each edge. But if you compute the random numbers, and if you take top K from them, then you are guaranteed to get K edges. And you can make the number of sampled items deterministic in this way. So here, let's see an example. So given seed vertices 1 and 2, let's say we can see that the degree of the first vertex is 3 and the degree of the second vertex is 4. And we want to sample 2 edges. So the thresholds we computed by computing K over ds for each, it's 2/3 for the first, 2/4 for the second. So we also roll random numbers for all the neighbors, and the random numbers have the property that we only roll it once for a given vertex, and they are shared if they are overlapping neighbors. So here we have the random numbers as an example. If we check if this edge is sampled, we see that it's not, because 0.7 is not less than or equal to 2/3. But for this edge, for example, we see that 0.4 is less than or equal to 2/4, so we sample this edge. So if we do it for all, we end up sampling these edges. And for any other random numbers, this could be different, but you can see that in doing it this way, we get really nice overlapping neighborhoods. Still, it's all unbiased. So how does the algorithm look like? So given a set of seed vertices capital S and Fn out K, what we do is we collect the union of the neighborhoods of those vertices in line 3. And then for each of those vertices, we roll the random numbers. And then for for all of the edges, we check if the random number is less than or equal to this threshold we compute. And if that's the case, we append it to the list of sampled edges. And this operation is actually corresponds to a copy if operation. Like if this condition holds true, then we copy it to an array. And if it's not true, then we skip it. And you can find parallel implementations of such algorithms in many common libraries. For example, if you're programming on the GPUs, for CUDA, there is these libraries called Trust or CUB. And there you can see like Trust has a copy if algorithm that automatically is accelerated on the GPU. Or if you're programming on the CPU, there is also algorithms available in the standard library of C++. So you can parallelize this algorithm very easily. So let's see some experimental results. So here, what we are looking at is the two data points we want to look at are the green and the brown, which correspond to the new algorithm that we talked about. And the NS stands for the independent way of performing this sampling operation. And here the x-axis is scaled with respect to the cumulative number of sampled vertices. And we can see that by using this new sampling algorithm, we can sample much fewer vertices. And if you measure how fast your convergence is with respect to how many vertices you are consuming, then you can see that it can be much faster. It can converge much faster, because like you see here, the green is much higher or on the left than the brown. And in terms of edge efficiency, we also have a similar picture. Here, the x-axis is scaled by how many edges are used for training. And we can see that by utilizing a better sampling algorithm, you can make GNN training faster in terms of how many edges you consume as well.
So I'm assuming the accuracy there is you take the feature vector and you pass it through an MLP head, right?
Yeah, so you do this, if you have 3 layers, you pass the messages, and then because you perform random sampling, this is all random, but in the end, you have some embeddings calculated for your seed vertices, and you have some type of loss function.
Yes.
And you have some type of task where you can measure the accuracy. So
My question is, why do we need to do like for example, if you're doing classification, I think Reddit classification, then if you take one node vertex, one node, and then just take its neighbor samples and then do it, why do you need to do layer-wise sampling? What are the other neighbor nodes that you take along with the node under consideration?
So for example, if your GNN model has 3 layers, and let's say you are a vertex in the Reddit graph, like you could be as a user, right? So in order to compute your output, because we have 3 layers, I need your neighbors, their neighbors, and their neighbors. So those are so when you are performing this, you get some edges and vertices in your sample subgraphs. And these plots are scaled with respect to how many vertices you consume or edges.
So basically the seed vertex are like NS of T. As in like there are K hop vertices from your source vertex.
Yeah.
Okay.
Yeah, that's right. And here we see how many vertices and edges were sampled with these different sampling algorithms. So for example, for neighbor sampling, because it performs these sampling operations independently, the growth is very fast. So from 1K to 10K to 68K to 167K for the independent way of doing sampling. But for our algorithm, the growth is much slower, as you can see. So that's why we are able to train our model much faster in terms of how many iterations per second, how many training iterations per second we are able to perform. And on the rightmost column, you can see that if you do your training with these different algorithms, the accuracy of the model you get, the quality of the model you get is just exactly the same. Because our algorithm is based on like it is unbiased and like it has some mathematical properties. And because that's the case, you can do your training fast while still keeping the same quality. Now I will talk a little about cooperative mini batching. So the motivation is that if you perform full batch training where you compute the outputs for all of your vertices in every training iteration, there's no redundant calculation because you do every computation only once. But if you do mini batch training and if you use mini batches, then you need repetitive calculations because the neighborhoods, the sampled neighborhoods of your mini batches will be overlapping over iterations. So for example, in one iteration, I might sample the neighborhood of 0, but because we do 3 hops, it will intersect with the neighborhood of another vertex in another iteration. So there's a lot of repetitive calculations and we want to reduce that. So how can we do that? So our contributions in this work are, we look at the work versus batch size relationship in GNN training. We take advantage of this relationship and propose a data and intra-layer parallelism method called cooperative mini batching. If we do the same thing in serial execution, then we get dependent mini batching, which reduces the repetitive calculations across training iterations. So let's have some background here as well. So the GNN equation is as follows. So to compute the output of S, we need its neighbors T. And given the messages coming from those neighbors, we input them into a function and we got our embedding. And when you perform graph sampling, you start with a set of seed vertices. In this case, it's S0. And as you do the recursive sampling operation, you take the union of the existing vertices you have along with the sampled neighborhood along with their sampled neighborhood to get the next layer's vertices. And the work of an epoch of training, like epoch means a pass over your data with batch size S0 is as follows. So the work is equal to the work in each layer, the sum of the work in each layer times how many training iterations you have. So if you have V vertices and if your batch size is S0, then you have V over S0 training iterations. And in each layer, the work can be measured by how many vertices you have. So you take the expectation over how many vertices you have in each layer. And you can see that this is expected to be greater than or equal to your mini batch size, which is greater than or equal to the work required for full batch training, which is L times V, which is the cost of full batch training. So to reduce this, you can utilize a larger batch size, but we will see how to utilize this relationship in the multi-GPU setting without changing the batch size. So the redundant work per layer L can be measured by this ratio, the expected number of vertices in layer L versus your mini batch size. So how does independent mini batching work? So each processing element, here it could be the GPU, starts with their own seed vertices as 0. And then they perform the sampling operations independently to get S1, S2, and SL if you have L layers. And then after that, all the GPUs independently perform the loading operation for the input features, and if you have edge features in your dataset, edge features for the sample subgraphs independently. All this is happening independently, in parallel. And then you perform the forward-backward operations also independently with no communication. But the problem here is you perform a lot of redundant computations across those GPUs because they are doing the same kind of thing, same work, because the S1 up to SL might be intersecting with each other across the GPUs. So because of that, there is a lot of redundant work being performed. So let's have an example here.
Sorry. So one GPU only computes one seed vertex.
Not one, but a mini batch, like a set of seed vertices.
Oh, okay.
Like S0 is like 1,000 vertices. And then you sample 10 for each, for example, then it becomes 10,000. Depending on how much overlap there is, it might be smaller than that, but after that you do the second layer, it becomes 100,000, for example. But if there is some overlap, it might be smaller than that. And for the third layer, like it can become 1 million.
So here, the redundancy lies in computation in different GPUs?
Yes, because we start with we start with different set of vertices on each GPU, but their neighborhoods S1 to SL might start overlapping because like in real world graphs, for example, you may have heard this, like in 6 hops you can get to anybody, right? So that kind of happening is that kind of thing is happening here. So if you have, let's say, 3 layers, there may be a lot of, like, maybe more than 25-30% of the vertices might be overlapping. So if you do all these operations independently and without any, like, eliminating the redundancy, then you will do a lot of wasted work, which will it will be slow. So our goal is to eliminate those redundancies in this work. So here we have an example. So the first GPU has 2 seed vertices, and from those 2 seed vertices, we have 4, and then we have 7 vertices in the second hop. And other GPU may have 2 other vertices, but you can see that the second and the third hops start to overlap. So what we have is this kind of picture where all the green edges are being computed redundantly across those GPUs, and also along with their endpoints. So for example, B, C, D, E, F, G, their features will be loaded twice, even though they are needed only once. So if you were to treat your GPUs as if they are a single GPU, you could get a lot of savings. So this is basically what I did. So I treated these GPUs as if they are like a huge single GPU, so that they don't have to perform these repetitive calculations at all.
Sorry, I'm a bit confused about this repetitive calculation. What exactly is the calculation? So I understand those edges as like a forward pass type of thing, right? So in this case, I understand, but like when we compute backward pass, then it wouldn't be the case, right? Because like those GPUs have different graphs, subgraphs, and the whole backward thing would be totally different, right?
I mean, it's not different. So
One more point to that, even if they're like, it's repetitive work, isn't that in a different context, like they might be considered, but with like the word test and the consideration might be different.
I don't get the question.
So say you have 2 vertices A and B, and then for that when you're sampling, you might have repeat vertices, but then they have different context, right? For one, you're training with A as in consideration, and the other one is B under consideration.
So the computation starts from here, from the left to the right. So all the values you calculate are dependent on the values on the left. So because of that, the values you compute in the middle, they are exactly the same, whether it's for GPU 0 or for GPU 1. So because that's the case, it is completely redundant calculation. And in the backward case, that's still the case. That's still the case. So does that answer your question? Like, because their inputs are the same, the calculated things are the same across GPUs too.
I think I just have some conceptual misunderstanding what exactly I understood on the calculation, because I get this forward pass we do from left to right. Yeah, it should be the same in this particular subgraph, but I cannot like right now imagine how exactly should it be same when we going back if the subgraphs are different.
Backward might be different, but in the end, you calculate, what you want to do is to calculate gradients for your model weights.
Yeah.
And what happens for that is you do a reduction. You do a reduction over all the vertices you have into the model weights. And when you perform such reduction, it ends up being the same. For example, if you have 2 different GPUs, and if they ended up sampling 2 different sets of neighborhoods, yes, the calculations will be different. But that's like wasted work. You could have just used the same neighborhood, for example, and do the same calculation. Maybe that's helpful.
I mean, the backward computation also would I mean, though it is different in the sense, when the gradients are split, the computation graph is just unrolled twice, right? So it will be, the gradients might change, will still remain the same, but it'll just be twice. I mean, based on the input.
So in the backward pass, the input becomes the right-hand side, right?
Right.
And then it flows to the left. And in that case, the numbers may be different, but
Like the loss might be different, but then the graph just unrolls twice, right?
yeah, something
Yeah,
like that.
yeah.
So you have the copy of this small section where the edges are green. It's copied
Yeah.
in the two GPUs. So that's the base of work. So, but if you were to treat your GPUs as if they are a single GPU, and if you were to treat this whole sampled subgraph as a single subgraph, then you could avoid those repetitive calculations by sending messages between the GPUs. You can see here there's a horizontal line, and any edge that cuts that line means that there is some type of communication happening between the GPUs we have. You may say, oh, because there's communication, it could be slow, but for some GNN models, the model computation is so expensive that that this communication, especially if you have NVLink on your system, is much faster than doing this computation twice. So we have two.
Can you go back to the previous slide? Yeah, so how do you consider them a single GPU? I mean, because for example, if B resides in GPU 0, and when you do computation on GPU 1, how does it know that B has resided in GPU 0?
I see. So here you can see a horizontal line, right? Everything at the top is on GPU 0, and everything at the bottom is on GPU 1. And whenever there is an edge crossing this boundary, there is a message going from one GPU to the other.
Okay, I see. So, so basically you just do a sharding.
It's just communication. You
Oh,
just
yeah,
send
yeah.
messages.
Yeah, okay, I see.
And it's very easy to do this in a very simple way. Like you can write a custom operator, and it can automatically, like if you do this forward calculation, it also automatically does the backward for you, for example. Like it just becomes another layer just to send these messages. So let's talk about some theorems we have in this work. So the work per epoch, which is this ratio we have, like the number of expected vertices in layer L over the bed size we have, required to train a GNN model is monotonically non-increasing as the bed size increases. And another theorem we have, it's kind of the same thing. The expected subgraph size required to train a GNN model using mini-batch training is a concave function of the bed size. So what do we mean by these? So here we have some plots. So on the top, you can see how many vertices are sampled per seed vertex. And at the bottom, you see how many vertices are sampled. And the x-axis changes how many seed vertices you have in your mini batch. So we can see that if we increase our batch size, the subgraph size, the expected subgraph size is concave, like it keeps flattening. And if you divide it by the mini batch size, then it is decreasing, which means that if you use a larger batch size, then you will save work. But our goal is to not increase the batch size. Our goal is to utilize multiple GPUs and save work. So how does it connect to that? So how it does is as follows. So if you have 8 GPUs, and if each of them has 1,000 batch size, if you keep them as independent, then it's as if then the work they are doing is characterized by the batch size 1,000. But if you were to treat them as a mega GPU, and then their batch becomes a mega batch of size 8,000, then the work they have to perform corresponds to the work of the batch size 8,000. So here what happens is, even though the global batch size we have is the same, we are basically moving from the batch size 1,000 to 8,000 in terms of how much work we need to perform. And because of this, you can get computational savings and runtime benefits. So let's see. Okay, here we have the pseudocode of our algorithm. So what we do is basically, so in the independent case, you can imagine all the all-to-all calls in this algorithm, they are not there. for the independent. Only for the cooperative way of doing this, we have these all-to-all calls. So what we do is, given some seed vertices, we do perform the sampling operation to get the edges and the next layer's vertices. And given those vertices, we perform an all-to-all operation so that each GPU gets the vertices that they are responsible for, and there is no redundancy. And this kind of pattern, so during the sampling, we have this kind of pattern. It is repeated for the forward and backward operation. So whatever kind of pattern we have in the sampling operation, it is repeated in the forward and backward computations. And that's basically the algorithm. So we have another algorithm that we are proposing in this work. So it's called dependent mini-batching. So the observation is that any parallel algorithm can be executed sequentially. So what you can do is, if you have, for example, an algorithm for 8 GPUs, let's say the GPU 0 performs some work, the GPU 1 performs some other work, you can perform it on the same GPU by performing the first GPU's work first and then the second GPU's work second in a sequential way. So it is easy to see that any parallel algorithm can be executed sequentially. So what we can do is, we can sample a mega batch of size kappa times beta. If the beta is the batch size and a kappa is an integer larger than 1, then we sample a mini batch, a large mini batch. And then what we do is, we extract kappa mini batches of size and beta from it. So what this achieves is, the sampled neighborhoods for kappa consecutive mini batches stay static because we have performed the sampling operations already. And from this sampled subgraph, we extract k different mini batches, and the edges can only come from the edges we have sampled, and it's already done. So those sampled neighborhoods for a given vertex stays static over kappa iterations. So one problem with this could be that, like, the sampled neighborhoods change instantly every kappa iteration. So how can you fix that? If you can make it change continuously, so you can evolve a graph continuously. So how can you do it? So the labor zero algorithm.
Wait, why does the sample neighborhoods change instantly every kappa iterations?
Because
We sample everything.
because when you perform the sampling operation for kappa times beta vertices, then the edges are already sampled. And if you extract kappa mini batches of size beta each from that, let's say there is some overlapping vertex in two different such mini batches, then their neighborhoods will be exactly the same. But if you were to do this separately for each mini batch you have, then they might have gotten different neighborhoods. And because of that, it's static and the same. And because of this, it's changing instantly across these kappa iterations. So these change instantly, so you can make it continuous in this way. So let's remember how this sampling algorithm worked. The edge T to S is sampled if this condition is true, if the random number we have is less than or equal to some threshold. And this random number comes from the uniform distribution. If you evolve the random numbers kappa times slower in your algorithm, then these neighborhoods will change smoothly across these kappa iterations instead of instantly. So so if you evolve your random numbers slower, then the neighborhoods will also change slower, and you will have a smooth change. And what this achieves is, across iterations, you get temporal access locality. So you will start to access some vertices much more because but we have seen that the work for a larger mini batch is smaller, right? So because of that, the exact same thing applies, and the stuff you access if you change the random numbers slower, you start to keep accessing the same things more and more. So for example, if you had a cache, then its hit rate keeps going up and up. So we will see such results. So here we have an example. So here we have the 1 and 2 neighbors again. And for k equal to 2, we have rolled some random numbers. And for those random numbers, we have sampled these vertices and edges, denoted in green. And in another iteration, we could have different set of random numbers. You can see that they are just like different. 0.7 for the first iteration, 0.5 for the second iteration for the vertex 3. And you can see it's different for the different vertices. And we end up getting, like because the random numbers are different, we got different neighborhood and different set of sampled edges. So
Therefore, we keep all the neighbors in the memory.
you can assume that this graph is stored somewhere and we are performing the sampling operation. So for example, if we want to sample for 1 and 2, we have to access the graph for 1 and 2 and access their neighborhoods and then perform the sampling operation.
But before loading them on GPU, right?
Hmm?
It's before loading them on GPU, right?
Yeah, before.
Okay. And I'm wondering why do we need this independent mini batch?
Oh, we will see.
You just said it's cache locality, data locality.
Yeah.
But if we really want to utilize data locality, I think we may need to load all the neighbors into the GPU.
Yeah, but your GPU memory is limited.
Oh, yeah.
All of them may not fit. But let's say you use some type of cache for the features, then you can only fit a portion of your data there. And if you had higher temporal locality, then this cache could be more effective. We will see the results in a bit.
Oh, okay.
So how can you make this smooth transition between the case between the case on the left and the case on the right? So if you look at the middle, you will see the random numbers we use are the average of the random numbers we use between these two different cases. And because the random numbers are the average, you get a smooth transition from the left to the right by going through the middle case. And you can see that the overlap of the middle case to the left is greater than the overlap between the left and the right. And the overlap of the middle case to the right is also greater than the overlap of the left and the right. So because of that, because we have more overlap across iterations, if we had a cache, then it could be more effective. So that's how it works. And there's like a simple formula using sines and cosines to do this continuous change on the random numbers. Like here we have the example of kappa equal to 2. So we have only one intermediate step between two different independent steps, but you could have any number of integer and you could have any number of in-between stages.
Really quick, I didn't get this overlap part. So you said that the one in the middle has both more than the on the left and on the right, right?
Not more, but the overlap of middle and left is larger than the overlap of left and right.
Yeah, okay.
So 4 and 5, 3, 5, 7, the overlap is only 1. But and you need 2 new vertices, right? Like 3 and 7 are new. But if you go through the middle, then first you need to load the 3, then you need to load the 7. So the number of new vertices you need are halved basically here. If you were caching this data in any way, let's say if you already had cached 4 and 5.
This is slightly off, but by doing this, wouldn't the learning slow down? Because you are kind of using the same sort of neighborhoods.
Yeah, we showed that it doesn't slow down much. I mean, it doesn't slow down and you get these benefits. So here we have the experimental results. So here, the different curves correspond to different kappa values. So if the kappa value is large, it means this random neighbors you use change that much slower. They become independent every, let's say here we have the 256. For 256, the random numbers become totally independent every 256 iterations. And we have also infinity here. And for infinity, the random numbers never change. So we see that if you never change those random numbers, keep using the same random numbers for the vertices you have in your graph, then you get bad results. But if they change 256 times slower, the convergence doesn't seem to be affected at all. And you can see that we have a cache to load the features for the sample vertices in our graph. If you perform this change slower, you can reduce the cache miss rates a lot. So here you see, for example, for the papers data set, the cache miss rate for the vertex features, it was above 60%. But after slowing down this change, it became around 30%. So we saved 2 times bandwidth. Like, for example, if this cache is on the GPU, for example, and if something is missing, then you need to perform a copy from the RAM through the PCIe to the GPU. And because the cache miss here is smaller, you need to transfer less data, which corresponds to faster runtime. And you can see that the curves are basically inside each other, meaning that our model training doesn't get affected at all. So we have the runtime results here on 3 different systems. So one system has 4 A100 GPUs, the other system has 8 A100 GPUs, and the other one has 16 V100 GPUs. And here you can see the properties of these GPUs. So gamma is the global memory bandwidth of the GPU, alpha is the NVLink bandwidth, beta is the PCIe bandwidth, and S0 is the global bit size that we use for training. And here, the IC column stands for whether we perform the independent way of doing the training or the cooperative way of doing the training. And we can see that for the graph sampling operation, so for the graph sampling operation, what happens here is the GPUs are accessing the graph in the system memory. So these accesses are happening over the PCIe. So because that's the case, when we use cooperative mini batching, the runtime goes down because we have to perform fewer accesses over the PCIe because there is overlap. And for the feature copy, the same is true. The features are stored on the RAM, and the GPUs are accessing these features through the PCIe. And because we don't perform redundant copies, we only copy everything only once. And once you copy them, then you can have the communication between the GPUs. The feature copy operation also becomes faster. And you can see that if you have a cache, or if you have a cache and use the dependency algorithm, then you can see that the runtime becomes faster and faster. And in the end, we see that the total runtime is much better for cooperative mini batching across different use cases than independent mini batching.
What are those numbers? Is it seconds, minutes,
Milliseconds.
milliseconds?
Yeah. For each training iteration. Like you perform 100,000 of these, or maybe even more, when you're training a GNN model.
Oh, we can combine those 2 optimizations together.
Yeah.
One is kappa.
Yeah, exactly. The cooperative one, along with the kappa cache one, is the combined version.
Oh, yeah, but I think using kappa, we are reducing the batch size in 1 iteration. And
We are not.
we are not, but we divide a big batch size into kappa slices.
Yes, like you can think of it this way. So when you use the kappa trick, if kappa is larger than 1, then you have correlation across iterations, meaning overlap across iterations.
Yes.
But the batch size and everything is still the same.
Okay.
What is the kappa value there? Like,
Here it's 256. So for example, you can see here that even if you use 256 or 64, it doesn't really matter. So, and the convergence is the same too. I just use 256. So we had a lot of numbers there, and you couldn't get a lot of information from those numbers. But if you compile those numbers and look at the speedups you get across different machines, you have these following results. So if you have 4 GPUs, then if you do cooperative mini batching instead of independent mini batching, you can save around 20% runtime. If you have 8 GPUs, then you can save up to 36%. And if you have 16 GPUs, you can save up to 64% runtime. Why is the speed up going up as we increase the number of GPUs?
Because there's less overlap, because, I mean, there's more overlap, so.
Yeah, if you have
there are-
16 GPUs, they each have their own neighborhood, right?
And then the overlap is more.
There's more overlap, there's more redundant work being done. So that's why the speed up keeps going up. Okay, so let's summarize our findings. So we can reduce the work with this new cooperative mini batching algorithm for GNNs. And another thing is that like we skipped over it, but like there were two different GNN models in my results. One is the GCN and the other is RGCN. And RGCN is an expensive model, and as you can see that the forward backward iterations, let's say if you look at these two numbers, independent mini batching is faster than cooperative mini batching for the forward backward stage, because the GPUs don't have to perform communication there, and because the model is already so cheap that you can recompute those things and still be faster. But if you use a more expensive model, such as the RGCM model, we can see that cooperative mini batching is faster than independent mini batching, which is because the model is more expensive now. So recomputing those things, it's slower than just sending messages between the GPUs. So cooperative mini batching is more effective if you have a more expensive GNN model. So if the forward is expensive, then you are allowed, like you can send messages between the GPUs to avoid those expensive computations.
Then wouldn't the difference be more in the RGCN model compared to the GCN model?
Let's look,
Like,
for example,
like for the first,
here 172 versus 200 versus 183 versus 200. So from 183 to 172 on the same GPU, it is becoming faster.
right, but I see. I mean, I was comparing it with like the GCNC. For example, in the first case, it's like from 8.9 to 13. The ratio, like the percentage of decrease because of using it is more than what you see in an RGCN model.
I don't quite understand.
No, like in a GCN model, like the forward backward, it's more simpler,
Yeah, it's simpler and less expensive.
less expensive. So message passing would be the overhead there. But then for an RGCN, just the GCN computations would be more expensive.
Yeah.
So message passing should be cheaper. So shouldn't the forward backward be like the difference, shouldn't that be higher like there than compared to the? Oh, okay. I think I got it. Yeah, I got it.
So what were we saying? So in order for this to work though, the GPUs or the processing elements you have on your system need to have really fast all-to-all communication. Otherwise, you will have a lot of overhead and it is just gonna slow down. And finally, if you have to perform less work, it will be faster. So like that's the takeaway message here. And finally, I will talk about the Python package I'm building with the AWS Shanghai AI Lab. It's called dgl.graphbolt. So how can we make an efficient GNN data loading framework? So there are, as before, there are three different stages: graph sampling, and we could potentially cache the graph on the accelerator so that the accesses to the graph could be faster. Feature loading, so we can cache some of the features on your accelerator, and the system memory. Sometimes the features are so large that it doesn't even fit your RAM. You have to keep them on your disk. And finally, you need to perform the forward-backward calculations on your GPU. But the problem is, because you have so much data, it doesn't fit on your GPU. Like maybe your graph will fit on your system memory, but the features may not even fit your RAM. So you might have to store it on the disk. So how can you make this pipeline from the disk or the RAM to the GPU fast? How can you make it? So here we have the pseudocode of an optimized cooperative mini batching algorithm. So how it works is, again, we are given some seed vertices. So what we do is we assume that we have some type of cache on the GPU for the graph. So given the seed vertices, what we do first is we check the cache. Are the neighborhoods of these vertices in your cache? Some will be there, but some will be missing. For the missing stuff, we have to perform a loading operation over the PCIe from the RAM. So here, line 5, we use the co-await keyword, meaning that this operation could, like, if you have done asynchronous programming before, the co-await stands for an asynchronous call. So when you do it, like, you don't have to wait for this operation to finish. Next, now that we have fetched the vertex neighborhoods from the storage, we perform the sampling operation, and next we have to perform an all-to-all operation so that each GPU can receive the vertices they are responsible for, and so that there's no redundancy.
So earlier you mentioned like GPU to GPU communication is like 300 Gbps.
300, yes.
Yeah. So GPU, do they have, like, when you say they have multiple GPUs, do they have shared cache?
There is no shared cache.
So when a neighbor is not in the cache of a GPU, instead of loading it from PCIe, would you want to check in the cache of other GPU?
So the way it works is we perform a logical partitioning of the vertices. Like, let's say every vertex ID, like if you perform, let's say, a mod operation, let's say if you have 8 GPUs, if the vertex ID mod 8 is 1, then what we do is we always send the seed vertex that is mod 1 to the first GPU, so that the cache is like combined cache. Like if the GPUs have a cache, there's no redundancy across the GPUs. So that way it's like a single unified cache, just like a mega GPU, and the same kind of. So once we have fetched the missing stuff, then we perform the sampling operation, and next we have to perform an all-to-all operation. But what we don't want is to wait for all these slow operations. So for example, line 5 performs a copy operation across the PCIe. Line 7 performs a copy operation over the NVLink. These are different hardware components. And 6, for example, line 6 performs a computation on the GPU. So what you want is you want to have all these different hardware components running in parallel with each other. But how can you do it? Like, the output of 5 is needed to perform 6, and the output of 6 is required to perform line 7. So what you can do is you can perform pipelining. So what you can do is, like, you can have mini batches coming in, and whenever you have a co-await keyword, you can have a pipelining stage, so that you don't have to wait for the operation to complete, so that you can switch to the next mini batch. Like for example, while we are loading for the while we are fetching the graph data on line 5, I can perform the operation for the line 4 for another mini batch, for example. So you can perform pipelining, and if you do it this way, then you can keep your PCIe copies running in parallel with your NVLink copy operations running in parallel with any computation on the GPU running in parallel with any computation on the CPU. So every hardware component you have, if you utilize pipeline parallelism, can be running at the same time, so that you can utilize the hardware you have efficiently. And finally, for the feature loading, it's the same thing. So we have some vertices. We want to fetch those features. We check our cache. If it's not there, we load the missing stuff from the PCIe, and then we do the all-to-all. But like, you need to perform pipeline. You need to have pipelining stages so that these steps don't wait for each other. So how does this look like? How do you use this kind of thing in Python? So here we see dgl.graphbolt, how to construct a data loader. So given the graph features some set of seed vertices, batch size, fan out is the K in the slide. So it could be 10, for example, 10 vertices, 10 neighbors for each vertex, and a device. So what we do is, given some training vertices, for example, we give it to the item sampler with batch size, and we say that we want to shuffle so that we get random neighborhoods. And then we get a data pipe from that. And to this data pipe, we say, let's copy all these to the GPU. After that, we say that we want to perform the sampling operation. I think someone needs to move this area. So after everything is on the GPU, after our seed vertices are on the GPU, we want to perform the sampling operation. Here, sample layer neighbor says that I want to perform, fan out could be like 10, 10, 10, meaning that we want 10 random neighbors in each layer. So sample layer neighbor step says that I want to have like 3 layers, and in each layer, I want 10 random numbers for my vertices. And then after that, we have the feature fetch operation. So given features, I want to fetch the feature with the key called feed, for example. And then after that, you get a data pipe, you give it to a data loader, and this is your data loader. But here, none of these operations are running. So what we are doing is we are describing what should be running, right? So when you do that, what you can do is, now that you know what you need to do, you can analyze this and modify it. Like, for example, if some fetching operation is needed, then I can like do this in a pipeline way or things like that. So how can we do that? So this, after you run that code, you get this kind of chain of operations. So here we have at the top the item sampler. This is a bit hard to read, but we have the item sampler, and then after that, we perform the sampling operation for the first layer. Then there's a compaction operation so that you compact so that like there might be overlapping vertices sampled. If you compact them, unique them, so then you don't have to perform sampling for the same vertex twice. So we have the sampling, compact, sample, compact, sample, compact, meaning we have 3 layers. It is repeated 3 times, and then this forms the neighbor sampling operation. After that, we have the feature fetching operation. So the red is the neighbor sample neighbors step, and then the green is the feature fetching step. So we have this kind of pipe, right? So in order to make this go fast, we need to perform some optimizations. So let's talk about how we can make feature fetching faster. So features is a huge tensor stored on the CPU. And we want to perform this calculation basically. From features, we want to index some vertices, and then we want to move them to the GPU. So like if you just run it this way, it's first gonna index on the CPU, then move to the GPU. But this is happening in 2 steps, meaning that we touch the same data twice, like first to index, then to copy. Like this could be slow. What we can do, can we do it better? So GPUs are made of streaming multiprocessors, similar to cores in CPUs, and CUDA streams are queues to schedule work to GPUs. And if the work launched in a stream doesn't occupy all of your GPU, then the work from another stream can run at the same time. So what we want to do is we want to perform this operation, right? So we can do this. So there is an operation called page locking operation. What it does is it ensures that your features are page locked in your memory so that they are always guaranteed to be there. That way, you can give a CPU pointer to the GPU, and the GPU can access your RAM directly. So what you can do is you can pin the memory for the features, then the GPU can directly access the RAM and perform this copy operation, like index and the copy in a single kernel, meaning that the CPU doesn't have to do anything at all. It happens in a single touch. And actually, GPUs have hundreds of thousands of threads, and only 6,000 of them are enough to saturate the PCIe bandwidth. Meaning that when you're performing this operation, you can actually perform other calculation. So if you were to use separate CUDA streams, you can overlap the PCIe copies with the other computations. So how can we do this? We set a limit on the copy operation, let's say 6,000. And then we find all the feature fetching operations in that graph we had before. And for all of those feature fetching operations, we replace it with So we set a different stream. We say that the feature fetch should run on another stream, and then we add a buffer and a wait operation so that we have a pipelining stage there, so that this step can happen in a pipeline way. So the change looks like this. So before we had the feature fetcher, but now we have these two steps added. And because we had the description, like we can do anything to it. So you can do this without the user noticing anything. Seamless optimization. And you can do the same thing for the graph fetch operation. And what you do is you again set the number of threads for the copies, and you find all the sampling operations in each layer, and you replace them with first fetching the graph neighborhood, then performing sampling. And between the fetching and the sampling operation, you can have a pipeline state. So it looks like this. So first you fetch the data, then you have a buffer and the wait operation, which means we are inserting a pipeline stage there, so that the fetch operation and the rest of the operations can run at the same time. So meaning like we had a sample and the compact, but now sample becomes like a chain of other operations to do pipeline. So what is the result? The result is we get very good runtime. So compared to the existing state of the art, we can get, for example, just compared to using the CPU, we can get up to 4 times speed up. And compared to the existing state of the art, we can get a lot more speed up on the node classification task for different data sets. And for the link prediction, the same picture is there. We can get up to 5 times speed up. And on the multi-GPU, because the CPU is shared by the GPUs, the CPU-based data loading doesn't scale. And if you perform the data loading on the GPUs, you can get more than 11 times speed up compared to the CPU way of doing it. And this is a comparison against PyG, and we can see that our GPU accelerated operations are much faster, up to 5 times. And I think I'm out of time, but I was gonna talk about like how to insert the cooperative mini batching operations. We had all to all, right? So what you do is basically you find where you need to do that operation and you insert it there. That's it. So that's it. Thank you for listening to my talk today. I hope you were able to learn something, even though my topic is a bit focused. It's like specific, a very specific topic. I hope that some of the things I have done will give you ideas for your future projects. Thank you. Thank you.
I really like the G and the G.
If there are any additional questions, I can answer them.
There's that, like, I'm used to the LG gram. Well. Oh, really? Not really. It's good. It was really swift. I don't really give much, but I really give
Like, you said, so most of this just works because of like ending the memory.
Yeah.
And then because deep in the memory, the CPU can fetch the work, like, tutor to use like older versions.
So you can get like
Or like
USB-C.
the other ones can
chargers
just use
and
other
you
versions and then they can just pipeline this like.
And then just better.
Like it's similar to like.
Hitting the memory makes it like, normally you
Yeah.
use pointers
Grab a-
to point to data, right? And
You-
the pointer might point to
This is just the
some
derivative.
location in RAM,
So it's
or
not-
it could point to some location on the GPU. But even if it points to the RAM, if you pin the memory,
Yeah,
you
yeah.
can
it's like
access
bring
it
some
directly from the GPU.
GNN.
Meaning that the CPU doesn't have to do anything. Like if you have some features and if you want to index them and fetch them, you can just give the pointer to your kernel and launch a kernel on your GPU,
I
which
see.
does this access, and it just works. But it's slower, of course, because
I
this access
totally
is
gave
opening,
up on this.
this access is happening on the PCIe. So it's much slower, but it's faster than doing it on the CPU.
There is now.
Then-
Sorry.
No,
Why is that?
oh, yeah, but like.
What was the
this,
reason you used like, why
Simon,
did you use
that
like
just
algebraic
happened.
geometry?
Yeah.
What was the reason you chose
I'm
like?
taking the class
BGL?
pass fail, so it doesn't
Oh,
matter.
because,
Yeah.
yeah, already had some.
wise decision.
Acceleration for the loading stage.
I wanna learn the
in,
concept.
when I was
but I also
at
don't want
Air
to
Neighbor
graduate.
I
Yeah, so
like looked at how they
This
summer.
implemented
Yeah,
neighbor
so
sampler.
that's weird, but I was like, if I
Independent way
do
of
take the
sampling
class
on the
non-pass
GPU,
fail, then I'll
And I was
graduate.
inspired by it.
So I was like,
to
"Ah,
my own GPU.
see what my hardest class
Like
this
it's a different
semester
algorithm,
is,
but
then
I
switch to
accelerated it
pass
for
fail.
for DGL. But you like 1 year passed and
Yeah,
they noticed
I
that
just need to get a 70.
this existing data
Yeah,
loading
so-
code is
and then
not
each homework is
maintained.
only
They
5
decided that we
points.
should not,
The final project weights
Oh, I
like
see.
which is
Yeah,
DGL.
exactly, but
But
I was like,
have the expertise.
dude, I
Yeah,
put so much time into the homework.
skip the MPI one.
Yeah, I was like, dude, I think I was on like hour 20
I am the one
working on it, like
responsible.
straight, and then I was like still getting seg faults. I was like, I give up. I didn't wait like.
I'm also implementing all these pipeline optimizations and things like that. According to my PhD thesis. So the design of this package from an optimization perspective, it forms my PhD thesis.
Okay.
You can reach out to me later.
At 5 points.
Yeah, yeah.
I'm just saying. That's a really good doggy. But I'm excited to be able to start working on the CUDA one. Make my mom feel a little less pain. What are you up to? Library, yeah, on the grind. No, go home and cook. I'm fasting right now.
Prepare yourself today.
But,
You prepare yourself today. You cook yourself.
oh yeah, I cook every day.
Cook every day.
Yeah, I try to.
Thank you for listening, everyone. Take care.
but-